Question 5. Name and outline mechanism for this reaction. 5.1. Excess of ammonia forming propylamine nucleophilic substitution. Nucleophilic. They really like this mechanism. Obviously, I'm going to go through it now, but they do really like this mechanism. I think I've seen it in A-level paper as well, not just AS papers. So what's going on? Well, since this is a propylamine by the reaction of this with excess ammonia, so 1 iodopropane CH3 CH2 CH2 iodine, right? And we've got ammonia, excess of ammonia, lone pair of electrons on N. Now, so carbon's partially positive, iodine's partially negative, and this lone pair of electrons are going to attack partially positive carbon. Ci bond breaks. Surely it can't be that easy, man. Is that maybe what you're thinking, guys? Yeah, it's not that easy. Now the next step, so it's just replace it, it's just been substituted. Nitrogen's positive, and we've got this I minus just floating around. It's not part of the molecule anymore. And now what's going to happen? Another ammonia molecule, but in this case, it's going to act as a base, take a proton, and then from rid of NH bond to the nitrogen. And then what you form is this. Nitrogen has lost one of its hydrogens, and now it's got lone pair of electrons. Transferred lone pair of electrons to that, and it's taken its hydrogen. And you also have now the NH4 plus ammonium ion. NH4 plus, aka the ammonium ion. And if you look at the equation of CH3, CH2, CH2, CH3, CH2, CH2, NH2, yes, plus NH4I, but we've only formed NH4 plus. Well, the I minus will then also later bond to the positive charge, that's positive, that's negative, to form NH4I, but that part they don't really care about. So you get this, attacks partially positive carbon, Ci bond breaks, then the NH3, the ammonium ion, takes proton, acts as a base, NH bond breaks, and that's all it wants, but you can show the forming of the product. I prefer to do that in case it does want that. That's I minus. And then 5.2, calculate the number of molecules in 50 centimeters cubed of 1 iodopropane, MOL 169.9. Give your answer in standard form. 1 iodopropane density is that, Avogadro's constant is that. Okay, we've got a lot of values for this, and it's only 2 marks. Number of molecules in this much of that. So to find out the number of molecules, we need to find moles, and we times it by Avogadro's constant. That's the first thing. How do we find the moles? We need to find out the mass. How do we find the mass? Well, we know density is equal to mass over volume. Mass is going to be density times by volume. Density of that, volume of that. 1.75 times by 5 will give me my mass as 8.75 in grams. And then we want to find out the moles. 8.75 divided by MR 169.9 0.0515 moles. And then to find out the number of molecules, it's going to be the moles times by Avogadro's constant, so times by 6.022 times by 10 power 23. That's why they gave it us in the question. Number of molecules is 3.10 times by 10 to the power 22. Okay, and then 5.3, in experiment, this much of iodo-propane reacted with this excess ammonia, this much is produced, calculate percentage yield in experiment. So percentage yield is actual yield or theoretical yield. Now, how would we do this? How would we actually do this? This is very tricky to marker. Well, we can find out the moles of iodo-propane, moles of propylamine, and we know the moles of propylamine is the actual yield. Okay, so that's all it's going to be. So we just need to show the working. So moles of this was going to be 10.3 mass over mR. Then we need to find out the moles of propylamine, that which is 2.3 divided by 59.0, and therefore the percentage yield is going to be this divided by the theoretical yield times by 100. So it's going to be 2.3 divided by 59.0 will give me 0.0390, and this will give me 0.0606. So all it's going to be is 0.0390 divided by 0.0606 times by 100, which will give me 64%. 0.0390 divided by 0.0606 times by 100, 64%. And that is the end of question 5.